Good morning, my name is Henrik Zwart and today I will be presenting REDstack and our advancement in electromembrane stack technology. We have developed a novel design that considerably improves efficiency and scalability, helping industries save on water, chemicals and operational costs. But before we dive into more technical details, let me give you a quick introduction on the history of REDstack. REDstack was founded in 2005 as a spin-off company from the Wetzel Institute. Our initial focus was on developing the reverse electrodialysis technology, also referred to as blue energy, where you generate electricity by mixing salt and fresh water. And our goal was to move this technology from lab scale to real-world implementation. To achieve this, we also started designing a highly efficient electromembrane stack for the energy production. And this resulted in a novel electromembrane stack design in 2020 that is energy efficient, leak-free and suitable for industrial production. At that moment, we also began exploring new market opportunities, since energy generation was still heavily relying on subsidies. Therefore, we presented our newly developed electromembrane stack platform technology at Aquatech, showcasing its applications in desalination, carbon capture and nitrogen recovery. Last year, we started engineering an automated production line and secured new funding to support our shift from R&D to full-scale production, aiming to deliver our solution to the industry which are dealing with these water challenges. Let's explore some of these applications. Currently, we are focusing on two main applications. First, electrodialysis reversal, or EDR, for the desalination of brackish water or water containing a low amount of total dissolved solids. But we are also exploring the implementation of EDR in brine treatment to achieve zero liquid discharge. The second application is electrodialysis with bipolar membrane, or EDBM. In this process, we use a special membrane to enable a range of chemical processes, including nitrogen recovery and carbon capture. I will go in detail later, but first a technical explanation on EDR, EDBM and our novel stack design. The ED stack consists of four components: anion exchange membranes, cation exchange membranes, spacers that separate the membranes and form compartments, and two electrodes. When the feed water flows through the stack and a potential is applied to the electrodes, the charged ions migrate towards the oppositely charged electrodes. As a result, ions move from one compartment to another, creating a concentrated stream and a diluted stream. The electrode polarity can also be reversed, which switches the dilute and concentrate compartment, reducing and preventing fouling and scaling inside of the stack. This is why this process is also referred to as electrodialysis reversal. The ED with bipolar membrane process is quite similar, but let's take a quick look at the differences. The main difference is the use of a bipolar membrane. The bipolar membrane is basically an anion exchange membrane and cation exchange membrane glued together. This prevents the direct transport of ions through it. Instead, ion transport is enabled through the process of water splitting. At the interface of the bipolar membrane, water molecules are split into protons and hydroxide ions. This creates an alkaline compartment and an acid compartment. This principle can be used to facilitate different chemical processes. I will give some examples later on, but let me now highlight why our electromembrane stack is truly unique. Here we can see our patented crossflow design on the left in comparison to a conventional plate and frame design on the right. In the conventional plate and frame design, the membrane surface is a red rectangle, where the flow distribution is integrated directly into the membrane area. as showcased by the dashed green line. This limits the effective use of the membrane surface and also complicates sealing of the different compartments. In contrast, REDstack crossflow design uses a square membrane surface, shown in the red square. And to maximize the use of the active membrane area, we have externalized the flow distribution, also highlighted by the green dashed line. This creates an inlet of one compartment on the bottom left and the outlet of that compartment on the top right, and creates our crossflow design. This approach also enables superior sealing between the two compartments and creates a highly energy efficient stack. But basically, we create these circular discs which contain a membrane package. Multiple discs are then assembled together to create the electromembrane stack. Depending on the required treatment capacity, more or fewer discs can be added. This modular design also makes it easy to replace individual discs for maintenance, and it allows the electromembrane stack to be completely leak-free internally and externally. I will now briefly summarize the advantages of our design again. Because of the crossflow design, 100% of the active membrane area is utilized. This also allows for superior sealing of the compartments and a watertight stack. Thanks to its unique design and these advantages, the electromembrane stack is highly energy efficient, achieving up to 50% lower energy consumption compared to conventional stacks. The EDR process itself also supports high water recovery rates and is resistant to fouling due to polarity reversal, and the patented flow distribution further minimizes fouling risks. So let's take a closer look at how these improvements in the stack design improve the performance compared to a conventional stack. For this comparison, I will specifically showcase the application of these stacks in desalination. Just to clarify, the name desalted refers to the REDstack's electromembrane stack for the desalination application. On the left you can see REDstack's electromembrane stack, and on the right a conventional plate and frame stack. To compare the performance, we tested both stacks with a range of salt concentrations and flow rates to evaluate the efficiency with different conditions. So let's take a closer look at these results. On the left you can see the graph showing the energy consumption versus the desalination rate. The red markers represent the data from a conventional plate and frame stack, while the blue markers show the result of the desalted stack. As expected, there is an increase in the energy consumption with an increase in salt rejection, because with EDR the required energy is directly related to the amount of salt that is removed. And these results are based on the desalination of feedwater with a TDS of 3000 ppm. And as we can see, the desalted stack shows approximately 2.5 times lower energy consumption compared to the conventional stack. In addition, we can see in the table on the right that the pressure drop of the desalted stack is also significantly lower, 100 millibar versus 450 millibar. This means that the REDstack design also has a lower hydraulic losses, resulting in lower energy consumption for pumping. And we have also verified the performance of the desalted stack with a case study. This case study was conducted at an industrial wastewater treatment facility, which treated the wastewater from 3 different paper mills. Due to the increasing restriction on groundwater extraction, a large-scale pilot project was launched for water reuse. This pilot also included the EDR technology, and the EDR pilot consisted of a 2-stage EDR system, where each stage could remove up to 60% of the salinity, resulting in an overall desalination of 80%. The results of the pilot showed that there was a stable performance with a fluctuating feedwater composition, and it was possible to achieve water recovery up to 95%. On average, there was an energy consumption below 0.15 kWh per cubic meter, and there was no need for maintenance or cleaning in place during the 6 months of operation. Let's take a closer look at this data. Here we can see a graph displaying the conductivity levels of the product water, feed water, and the concentrate over time. The system was operated with a set point for product water conductivity, which is shown by the orange markers. The dark blue markers represent the actual conductivity of the product water that was achieved during the operation. As you can see, even though there are fluctuations in the feed water conductivity, which is shown by the green markers, the system was still able to reach the product water conductivity set point. That means that the EDR system is very stable and reliable, even when the feed water quality changes. Here we can see another graph showing the water recovery, the desalination level, and energy consumption. During the pilot, several trials were carried out to determine the maximum achievable water recovery, which was found to be 95%, as you can see by the orange markers. The level of desalination, shown by the green markers, depended on the conductivity of the incoming feed water. And as expected, when the more salt had to be removed, the energy consumption increased, which is seen by the blue markers. However, even with this variation, the average energy consumption remained low. Now I would like to show you a comparison between the desalted and other technologies for this type of application. Here we can see a table highlighting some key parameters of desalination technologies. When comparing the desalted stack with a traditional plate and frame stack and the reverse osmosis technology, we can observe several advantages. Lower energy consumption, higher water recovery rate, reduced operational pressure, and a smaller installation footprint. And with this I will conclude the desalination part of this presentation. Now let's quickly explore two applications of the EDBM electromembrane stack in the field of resource recovery. The first application of the EDBM stack is in direct air capture for CO2 capture. In this process, EDBM plays a role by regenerating the alkaline sorbent used to capture CO2 from ambient air. This is an electrochemical alternative to traditional thermal regeneration methods. The second application of the EDBM stack is as an add-on solution for nitrogen stripping and recovery. This process offers an alternative to biological nitrogen removal. With the EDBM stack, the ammonium salt that is created within this process is converted into ammonium hydroxide, and the acid used for this is regenerated. This enables a closed loop and chemical-free operation. For now, this will cover the technical part of the presentation. Let's have a look at where REDstack as a company is headed next. The next step for REDstack is to scale up production. This will be achieved through the construction of an automated production line, which is expected to be completed by mid-2026. Once operational, this will enable us to produce up to 400 electromembrane stacks per year. In the meantime, we are actively identifying suitable projects to serve as real-world demonstration and reference cases. Finally, let me briefly explain how REDstack currently operates. At REDstack, we position ourselves as an OEM partner. We deliver electromembrane stacks that come with a basic engineering package to support integration and deployment. Our primary focus is on collaboration with system integrators and EPC contractors. At the same time, we of course also are engaging with end users because they help us explore new applications and identify what the market needs. So to end my presentation, my question to you is, how can REDstack support your industry in the transition toward climate adaptation, especially with our improved solution for salt removal in low TDS wastewater to achieve water reuse? Thank you for your attention.